Okay, good morning, everyone. So today we are back for our third lesson. So last lesson we went through ions and ionic bonding. So we know now that ionic bonds and an ionic compound is formed when a metal reacts with a non-metal. So metal plus non-metal is an ionic compound. And this is because metals lose valence electrons while non-metals gain valence electrons. Okay, so if you are lost, okay, please refer to the previous video, which is on ions and ionic bonding, where we actually went through how to draw the dot and cross diagrams for ionic compounds, as well as the physical properties of ionic compounds. Namely, that ionic compounds have a high melting and boiling point due to the strong electrostatic forces of attraction between the oppositely charged ions, which require a lot of energy to overcome, as well as ionic compounds do not conduct electricity in the solid state, whereas they will conduct electricity in the molten or aqueous states. So these are the characteristic properties of ionic compounds, which we have to remember that ionic compounds are formed between metals and non-metals. All right? So these are ionic compounds and ionic bonding, which you can refer to the previous video, JH2, for revision. So today we shall go on to covalent bonding. So as mentioned just now, ionic bonding is about losing and gaining valence electrons. Covalent bonding is formed not by loss or gain of valence electrons, but by sharing. So the keyword here is sharing of valence electrons. Now, which elements will share valence electrons with each other? So just now we said metal plus non-metal is ionic. So here, covalent is just between non-metals. All right? So it is the non-metals, the atoms of the non-metals, which will share valence electrons with each other. So let's begin by looking at a few diatomic molecules. You notice I have used the word molecule. Now, when we use the word molecule, it implies covalent bonding. So molecules contain covalent bonding. So molecules are formed by the sharing of valence electrons. All right. So what is the meaning of diatomic molecules? Diatomic molecules contain two atoms which are covalently bonded together. All right. So it's not just that there are two atoms, but the two atoms must be covalently bonded together through the sharing of valence electrons. All right. Now, we're going to start off with diatomic molecules. So the simplest diatomic molecule, of course, is hydrogen gas, H2. H2 is diatomic. I think this is quite straightforward to draw. Now, the moment you know it's sharing, it means that the valence electron shell must overlap. All right. The valence electrons overlap. This indicates sharing. So throughout today's lesson, you'll be seeing how the sharing works through the overlapping of the valence electron shell. Now, hydrogen has one electron only. Okay, hydrogen only has one electron. Therefore, it will share one valence electron with the other hydrogen atom. So we indicate this as one dot, one cross. So sharing one valence electron, we will draw it as one dot, one cross. Why? Because the hydrogen on the left will share its electron with the hydrogen on the right. Similarly, the hydrogen on the right will share its valence electron with the hydrogen on the left. So when we say share one, we mean that each atom shares one. All right? So we can say that each hydrogen atom shares one valence electron with the other hydrogen atom. Okay, and what is the purpose of sharing? Under ionic bonding, you have learned metals lose valence electrons, non-metals gain valence electrons in order to achieve a fully filled outer electron shell. So it is similar here. The sharing is such that it achieves a fully filled outermost electron shell. Now we have to bear in mind that hydrogen only has one electron in the first shell. So if you recall, under atomic structure you have learned, the first shell only contains a maximum of 2 electrons. Hence, by sharing the valence electron with another hydrogen atom, we now have 2 electrons which are shared. And 2 electrons, of course, makes the first shell fully filled. All right, so it is important to realize that the electrons which are shared, they are shared between the two atoms. So they are the common shared property of the two atoms. Okay, as a result of this, the valence shell is now full for hydrogen. Now we shall move on to other molecules, which are also diatomic. So we move on to HCl. All right, so again, we know hydrogen is a non-metal, chlorine, non-metal as well. So if it's two non-metals, it's covalent bonding. All right. Ken, so the moment you know it's covalent bonding, it has to be an overlap of the valence electron shell. Now, over here, we will show outer electrons only. The question will specify. The question will specify whether you need to show all electrons, including the ones in the inner shell, which are not shared, or do you only show outer electrons? So please read the question. This is from the question, stated in the question. All right. Now, so we have HCl. Again, it's not difficult because hydrogen only has one electron. Because hydrogen only has one electron, it can only share one electron with chlorine. If hydrogen shares one electron with chlorine, this means that chlorine will share one valence electron with hydrogen. All right. But we need to be slightly careful with chlorine. Chlorine, unlike hydrogen, has more than one electron in the outer shell. If you think of chlorine, chlorine is in group number 7. So if it's in group 7, it has 7 valence electrons, right? So chlorine should have 7 electrons in the outer shell. However, it has already shared 1. So we are left with 6 other electrons, which are not shared. So we need to bear in mind, chlorine has 7 valence electrons. It has already shared 1. Therefore, it should have 6 other valence electrons, which are not shared. Okay, so remember, Cl has a total of 7 valence electrons. 1 electron is shared with H. That means 6 electrons are not shared. Okay? So this is HCl. Now, this also makes sense because you realize now hydrogen, first shell has 2 electrons, right? After sharing with chlorine, okay, hydrogen will have 2 electrons in its first shell. Similarly, chlorine after sharing with hydrogen has a total of 1, 2, 3, 4, 5, 6, 7, 8. It is through sharing the valence electron with hydrogen that chlorine also has a fully filled outermost electron shell. Okay? And now we move on to other diatomic molecules like oxygen. Now, the oxygen gas that we breathe in is diatomic. So it's O2, meaning there are two oxygen atoms that are covalently bonded to each other. Now, we shall practice showing all electrons. Now, when we say all electrons, it means you need to show valence and inner shell. Okay, so we need to bear this in mind. You have to read the question. The question will state, do you show outer electrons only, or do you show all the electrons? So let's practice showing all the electrons. First, we know this is definitely going to be covalent bonding because we know oxygen is a non-metal. Non-metal plus non-metal forms covalent bonds through sharing of valence electrons. The way to do this is to do some working. First, we consider an oxygen atom. An oxygen atom has 8 electrons, meaning the electronic configuration is 2, 6. It has 6 valence electrons, which makes full sense because oxygen is found in group 6. Group 6 elements all have 6 valence electrons. Okay? Now, if it has 6 valence electrons, it needs 2 more electrons in order to achieve a fully filled outermost electron shell. 6 valence, it needs 2 more in order to be fully filled outermost electron shell. This means it will share 2 electrons. This is a key concept here. If you need 2 more electrons, you share 2 valence electrons. So what does sharing 2 look like? Just now, we did sharing 1. Sharing 1 with each other. So you share 1 with me, I share 1 back with you. So 1 dot, 1 cross. Sharing 2 is 1 dot, 1 cross, 1 dot, 1 cross. So what do you notice? 2 pairs of electrons are shared, right? 2 pairs. We call this 2 bonding pairs. Now, 2 pairs of electrons, of course, is a total of 4 electrons shared. 2 from each atom. Okay, so this is crucial. You need to realize that oxygen is in group 6, 6 valence electrons, it needs 2 more. If it needs 2 more electrons to achieve that fully filled outer electron shell, it needs to share 2 electrons. Sharing 2 electrons looks like this. 1 dot, 1 cross, 1 dot, 1 cross. So in total, you should have 2 pairs of 4 electrons which are shared. Next, we need to bear in mind the whole purpose is to achieve a fully filled outer electron shell. Oxygen is 2, 6, right? The second shell is the outer shell. I have already drawn 1, 2, 3, 4. 4 electrons shared, meaning I need to draw 4 more outside in order to make it a fully filled outer electron shell. All right. Now take note, we use different symbols for the electrons from each oxygen atom in order to make this clearer. All right, so we use a different symbol to represent the electrons from a different oxygen atom. Okay, this is just for clarity. Now, so I repeat, the first step is to establish that it's covalent bonding because it's a non-metal, non-metal. Next step is to work out how many valence electrons does each atom have. That will tell you how many more electrons it needs and therefore how many it will share. Once you have drawn the shared electrons, you must ensure the valence shell is fully filled. Fully filled means 8 electrons. So because there are already 4 electrons shared, we have to draw 4 more outside. This is true for every non-metal atom except for hydrogen. Hydrogen only has 1 shell. So the first shell, by sharing 1 electron, is automatically fully filled already. So hydrogen, don't need to worry. But for the other atoms like oxygen, chlorine, you must ensure that the outer shell has 8 electrons in total. Okay? Now, this is not the end yet. you must draw the inner shell. The 2 electrons in the inner shell should also be drawn. What do you notice? The inner shell electrons are not shared. Okay? So very often, they will ask you to count how many electrons are shared. In this case, 4 electrons are shared. But how many electrons are not shared? So let's count together. 1, 2, 3, 4. The 4 inner electrons are not shared. But those are not the only ones. 5, 6, 7, 8, 9, 10, 11, 12. So oxygen has a total of 12 electrons not shared or not involved in covalent bonding. So the ones highlighted in blue, those electrons highlighted in blue are not involved in covalent bonding. All right? So this is how we draw a diatomic molecule like oxygen. Okay? So I'll just give you a bit of time to ensure you have copied everything down. Okay, the next molecule that we're going to draw is another diatomic molecule, is nitrogen, N2. So again, we do the same. You know it's a non-metal, so definitely it's covalent bonding. Overlap the shells. All right? This time round, we shall show all electrons again. For practice. Remember, this is shown to you in the question. So please read the question. Do we draw all electrons or do we only draw the outer shell electrons? Now, we do the same steps. After you know it's covalent bonding, you try to work it out. Nitrogen is in group 5. Right? 5 valence electrons. So it needs 3 more. If it needs 3 more, it will share 3. So just now we saw, right? Sharing 1 is 1 dot 1 cross. Sharing 2, 1 dot 1 cross, 1 dot 1 cross. Sharing 3 will be basically 3 pairs. 3 pairs of electrons are shared. Again, 3 pairs is of course 6 electrons. Okay? Then final step, you must ensure the outer shell has a total of 8 electrons, except for hydrogen. Okay, other than hydrogen, every other non-metal atom should try to have 8 electrons in the outer shell after sharing. Okay, so this is how you would draw N2. And we're not done yet. We need to ensure that we draw the inner shell again. Do not forget the inner shell because you have to show all electrons. Okay? So again, if we were to count how many electrons are shared, the electrons shared are the ones in the overlapping region. That is 3 pairs of electrons shared or 6 electrons. But how many are not shared? So you have to count 1, 2, 3, 4. Not just that, 5, 6, 7, 8. So 8 electrons in total are not shared. That means they are not involved in covalent bonding. Okay? So based on these, we have already seen some clear properties and patterns in how to predict how many electrons will be shared. There's a pattern, right? For oxygen, it shares 2 electrons. Because it's in group 6, it needs 2 more electrons. Nitrogen shares 3 electrons. Because it's in group 5, it needs 3 more electrons. So we can now generalize. The group, how many electrons shared? All right. Group 7 will share 1 electron. All right. Typically, will share 1. Group 6 will share 2. Group 5 will share 3. All right. So typically, that will be the case. Of course, there may be exceptions for certain of these elements, but generally speaking, this is the typical trend. So as you saw just now, oxygen shares 2 because it's in group 6. Nitrogen shares 3 electrons because it's in group 5. Okay, so we have finished the diatomic molecules. Diatomic molecules contain 2 atoms which are covalently bonded together. Remember, the word molecule is only used for substances with covalent bonds inside them. Right? So now we have finished diatomics, we will move on to polyatomic molecules. So it's not just 2 atoms that will form covalent bonds with each other. We can also have polyatomic molecules. So as the name suggests, poly means many. So many atoms bonded covalently together. So how many is many? Just now we had diatomic. So now polyatomic basically means more than 2 atoms covalently bonded together. Okay? So we shall now draw some simple polyatomic molecules. The first one is H2O, water. Water is definitely containing covalent bonds. We say that water has a simple molecular structure. Okay, take note. The structure is called simple molecular, but the bond is called covalent bond. Now, a bond is a force of attraction. A structure is how it looks like. So water has a simple molecular structure. How will we draw the structure of water? First, when you are given a polyatomic molecule, you got to first decide what goes into the center. Because when you have more than 2 atoms covalently bonded together, something must go into the center, right? We will always choose the atom which is in the smallest amount. Smallest amount. So if you read the formula H2O, there's 2 hydrogen and 1 oxygen. So we choose oxygen to be the center. Okay, so now when I draw the molecule, oxygen should be the center. Hydrogen, hydrogen. All right, oxygen goes into the center, hydrogen goes to the side. So what do you notice? The hydrogen atoms have to all bond to the center. They all connect to the center. The hydrogen doesn't bond to each other. The hydrogens must bond to the center, which is oxygen. The next step is to try to work out how many electrons the side atoms will share. So after considering the center, now let's consider the ones at the sides, which is hydrogen in this case. How many electrons will hydrogen share? The answer is quite obvious. Hydrogen only has 1 electron, so it will share 1. And that's it, right? Sharing 1, so it's 1 dot 1 cross. Next, after considering the sides, you must fill in electrons to make sure outer shell is fully filled. All right. So hydrogen, no problem. Hydrogen, remember, only got 1 shell. So after sharing that 1 valence electron, hydrogen is fully filled automatically. So hydrogen, no need to worry. It's the oxygen, right? I've drawn 1, 2, 3, 4. 4 electrons are shared in total. So oxygen must have 1 more, 2 more, 3 more, 4 more. Remember, the magic number to make it fully filled is 8. So if you already have 4 electrons that are shared, you must draw 4 more outside, which are not involved in bonding. Now over here, Mr. So has only drawn the outer electrons only. Okay, so again, read the question. The question will specify, do you draw outer only, or do you also include the inner shell electrons for oxygen? Okay, so this is the structure of water. Now, this is the dot and cross diagram. Dot and cross diagrams are a way that we can use to represent the bonding present inside a molecule of water. Now, sometimes instead of drawing dot and cross, we will just draw this structure. Okay, now this is called the Lewis structure, named after the chemist who used this structure. Whereas the one on the left is called a dot and cross diagram. Okay, now the Lewis structure shows the covalent bond as a line. So every line, one line equals to one dot, one cross, meaning one pair of shared electrons. Again, one pair is 2 electrons. So again, very commonly in MCQs, they will ask you how many electrons are shared. They will give you the Lewis structure and ask you how many electrons are shared. You count. The number of lines equals to the number of pairs which are shared. So you bear in mind, one line is one pair. One pair is 2 electrons. So over here, I got one line, 2 lines. 2 bonds equals 2 pairs of shared electrons. Okay? Therefore, 4 electrons are shared in total in each molecule of water. All right? So that was H2O. Now let's move on to another commonly tested one, CO2, carbon dioxide. Now, carbon dioxide also definitely contains covalent bonds because carbon is a non-metal, oxygen is a non-metal, right? Now, the bonding is covalent bonding, but the structure is called a simple molecular structure as well. So please get used to these terms. Structure is simple molecular, but the bond is called a covalent bond. Now, so we are going to apply the same 3 steps. The first step is to determine what goes into the center. Just now, H2O only got 1 oxygen. That's why oxygen goes into the center. For carbon dioxide, CO2, will it still be oxygen? Right? So remember, the center is always the atom that is in the smallest amount. So in this case, I only have 1 carbon atom, 2 oxygen atoms. So 1 carbon, smaller number, smaller amount of atoms. Therefore, carbon goes into the center. Okay, let me draw my shells a bit nicer. Okay, so carbon goes into the center. Remember, once you have fixed the center, the side atoms must all connect to the center. So oxygen connects to carbon. The oxygens do not connect to each other. Oxygens connect to carbon. Now, the next step is to consider how many electrons will the side atoms share, right? So now we got to consider how many electrons will the side atoms share with each other. The ones at the side is oxygen. Just now we went through oxygen, we can predict how many electrons it will share because there's a pattern, right? Group 6 shares 2. So we are going to apply this now. Oxygen is in group 6, share 2. Share 2 is 1 dot 1 cross, 1 dot 1 cross. Same with the other side. Okay, finally, you must make sure that outer shell is full. So we have already drawn 4 electrons, so we must draw 4 more. Okay, so in this case, we use crosses to represent the electrons of oxygen. Dot will represent the electrons of carbon. Okay, now I'm not done. you need to ensure that you read the question. Does the question want me to show outer electrons only? If the question wants outer electrons only, this is already the correct answer, because I know that the outer electron shell of oxygen has 8 electrons. Similarly, the outer electron shell of carbon also has 8 electrons, because 1, 2, 3, 4, 5, 6, 7, 8. Remember, the shared electrons are the common property of the two atoms. So carbon already has 8 electrons in the outer shell. So if I was asked for outer electrons only, this is correct already. However, what if the question asks me to show all electrons? If that's the case, I will still need to draw the inner shell. Remember, the inner shell is not shared, so you do not overlap it. Cross represents the electrons of oxygen, dot represents the electrons of carbon. All right, so to show all electrons, this will become the correct answer, because you need to show the 2 electrons which are in the inner shell. Now we are able to draw the Lewis diagram as well. This time round, you must be careful, because oxygen shares 2 electrons. So there are 2 pairs of electrons shared. 2 pairs, 2 lines. So this is a double bond. So CO2 contains a double bond between carbon and oxygen. All right, Ken? Now, so we say that oxygen, each oxygen atom shares 2 valence electrons with the carbon atom. The carbon atom shares a total of 4 valence electrons with the 2 oxygen atoms. Okay, so writing out in words, this is how we describe it in words. Hence, each atom achieves a fully filled outermost electron shell. Okay, so you must also be good at describing this in words. How many electrons are shared? Okay, so it's easier to describe it this way. All right, so please ensure that you take this down, the dot and cross diagram, the Lewis structure, as well as the description. All right. Okay, now we shall continue with the physical properties of covalent substances. So we describe them as covalent substances. Covalent substances have a simple molecular structure. So we do not say, this is wrong, H2O is covalent bond. This is wrong. We do not say that it is a covalent bond. Why is this wrong? A bond is a force, of attraction. So in this case, a covalent bond is a force of attraction between shared electrons and the nuclei of the 2 atoms. So it is wrong to say that H2O is a bond. H2O is not a force. H2O is a molecule, right? So what is the correct way to say it? H2O has a simple molecular structure. Okay, we instead say H2O has a simple molecular structure. That is a correct way of saying it. Never ever say that a molecule is a bond. Doesn't make sense. Okay, remember, a bond is a force. All right. Now, so H2O, CO2, HCl, they are all simple molecular structures. Therefore, they have certain properties, such as low melting point and boiling point. All right. Typically, simple molecular substances will have a very low melting and boiling point. Now, why is that the case? Now, this is important. Many students think that, oh, does that mean covalent bonding is weak? It's not. It is not the covalent bonds which are being overcome. It is instead the weak intermolecular forces. There are weak intermolecular forces of attraction between the molecules. So if I were to draw H2O, this is one molecule, this is another molecule, right? The weak intermolecular forces are between the molecules. So this is the weak intermolecular force. So it's in between the molecules which you have the weak intermolecular forces of attraction. Therefore, when you are melting or you are boiling water, what you are doing is that you are moving the molecules further apart. You are not separating the oxygen and hydrogen atoms. You are not separating the atoms which are covalently bonded. What you are separating is each individual molecule only. Right? So what you are overcoming is the weak intermolecular forces of attraction. Thus, little energy is needed to overcome the weak intermolecular forces of attraction. Okay, if you need little energy to overcome the weak intermolecular forces of attraction, this means that you don't need so much heat energy. So don't need to heat it up so much to a high temperature. Even at a low temperature, there is sufficient energy to overcome the weak intermolecular forces of attraction. All right. So please have this visual picture in your head. What you are doing is that you are just moving each individual molecule further apart. You are not separating the atoms. You are not separating the H and the O that's bonded covalently into each other. What you are separating is just the molecules. Therefore, you are overcoming the weak intermolecular forces of attraction. Now, because simple molecular substances have a low melting and boiling point, what it means is that most of them will exist as either liquids or gases because they would have melted or boiled at room temperature already. Their melting point and boiling point is below room temperature. So most of them are either liquids or gases, which makes sense. Water is a liquid. Oxygen, O2, is a gas at room temperature. All right. So we say that the substances are volatile. Now, what does this word volatile mean? Volatile means that they vaporize easily. i.e., this means that they have a low boiling point. So for example, we will say that HCl is volatile. Oxygen gas is volatile. CO2 is volatile. All right. Now, all simple molecular substances tend to be volatile, including the ones that you just learned in organic chemistry, alkanes. Alkanes are simple molecular substances because they contain carbon and hydrogen, which obviously are non-metals, so alkanes are simple molecular substances. Therefore, alkanes are also volatile. Alkanes vaporize easily, they have a low boiling point. All right, so that's the first important physical property of a simple molecular substance. The next property that we talked about is always electrical conductivity. So, simple molecular substances do not conduct electricity in any state So this is different from ionic compounds. Ionic compounds will conduct electricity, okay, in the molten and aqueous state. However, for simple molecular substances, they do not conduct electricity at all, regardless of the state of matter. Now, why is this the case? Remember, electricity relies on charged particles that are free to move. If you were to look at a simple molecular structure, there are no free moving charged particles. So we say that there are no free moving ions or electrons. All right, so in water, in CO2, there are no free moving ions or electrons that can enable the substance to conduct electricity. Okay, so this is different from an ionic compound. Ionic compounds have ions which are free to move in the molten state, aqueous state. However, for simple molecular substances, totally no ions that are free to move, totally no electrons which are free to move. Okay, the only electrons there are all confined to either the covalent bonds or to the atoms themselves. Okay, now the world is of course not so simple. There is an exception to this. Okay, there are some simple molecular substances which are able to conduct electricity in certain states. So let's go through some of these exceptions. The first exception is familiar to you. It's HCl in the aqueous state. HCl has two names. The first name is called hydrogen chloride. Hydrogen chloride, HCl. That is if it's a gas. HCl gas is called hydrogen chloride. However, HCl aqueous is called hydrochloric acid. The next exception that is familiar also is HNO3 aqueous. HNO3 is called nitric acid. Right? So why do you think these are exceptions? These are exceptions obviously because they are acids. So in the aqueous state, they will produce H plus ions. Remember, acids are substances which produce H plus ions when dissolved in water. Okay, so these ions are free to move. Okay, so in the aqueous state, HCl, HNO3, they will conduct electricity because they produce H plus ions which are free to move in the aqueous state. Now, obviously, these are not the only acids. I am just demonstrating to you some acids. Okay, there are many other acids, including sulfuric acid, H2SO4, and we will learn some organic acids, carboxylic acids later on as well. All right. So these acids, they are able to actually conduct electricity in the aqueous state. Now, besides acids, we also have alkalis, notably ammonia. Right? Ammonia, when it's dissolved in water, it reacts to form OH minus ions. And that's the reason why ammonia, when it's in the aqueous state, also has free moving ions. So aqueous ammonia should be a good conductor of electricity. So these are the exceptions. The acidic substances and the alkaline substances, which are able to produce ions when they are dissolved in water. So these will have free moving ions in the aqueous state only. Aqueous state only, which will allow it to conduct electricity. Okay. Okay, so these exceptions, please try to remember these exceptions and be aware of this because this links very well to the chapter on acids and bases as well. All right, so today we have really covered what is a covalent bond. A covalent bond is formed by the sharing of valence electrons between two non-metal atoms. All right, we have learned how to draw dot and cross diagrams for diatomic and polyatomic molecules. All right, finally, we have also went through the physical properties of simple molecular substances. All right, there's one more physical property that I would like to highlight to you, which is generally simple molecular substances are generally soluble in organic solvents. Okay, for example, they can dissolve very well in oil, hexane. These are examples of organic solvents. So they are generally soluble in organic solvents, okay? Which is the opposite of ionic compounds. Ionic compounds do not dissolve in organic solvents. So we have basically summarized all the physical properties that you need to know. We have summarized the steps involved in drawing the dot and cross diagrams for both ionic and covalent substances over this lesson and the previous lesson. Now, a summary of this can also be found in the summary notes given to you at the start of the year, on the first day of school. If you recall, I gave you a very thick stack of summary notes for Sec 3 topics. You can also find these summary notes under our OneNote contents library under Sec 3 topics, summaries. And this is chapter 6. So chapter 6 summary is only 2 pages. It summarizes what you need to know about ionic and covalent bonding, about the giant ionic lattice structure, and the simple molecular structure. All right, including the properties which are shown to you. Okay, as well as the explanations. So if you are lost at any point in time, please refer back to this video as well as the summary, which can be found under the Contents Library, Sec 3 Topics, Chapter 6, Chemical Bonding. All right, and that brings us to the end of this lesson. And this means that we have already revised Chapter 5, Atomic Structure, as well as Chapter 6, Chemical Bonding. Now, next week, we will be revising how to write chemical equations and also QA before we start term 3 again. Okay, thank you for attending lessons, and I hope to see you next lesson.